There's often lots of confusion between this symbol and this symbol and this. What is the relationship between all three? The mean, this is the mean of this distribution you see right here, which can be calculated, and I came up with negative 0.5. That's the mean of this distribution. This mean is the result of sampling from this distribution for a fixed sample size and then calculating the average. So it's the mean of the distribution of all possible sample averages, while this represents an actual sample average. If I sample twice, here's the result of sampling twice. Here are all the possible sums. Of sampling twice. And if I want to create the distribution of the sample average, all I need to do is the following. I'm going to automate this. Just take this value and divide it by 2, since this is a result of adding two things. And we can see there's 1, 2, 3, 4, 5, 6 possible averages. That's X bar. This is X bar. This is X bar. This is X bar, X bar, X bar. So I'm going to change the symbols here. This is a result of adding twice and dividing by 2. Or this is X bar. And you notice we'll only sample twice. The fact that I use these probabilities to come up with these other probabilities means that this sampling process is unbiased. So what is the mean of this distribution? Let's just go through the process. I'm going to just now sum here. And I get negative 0.5. In other words, look, it's the same. This E of X belongs to this symbol, while this one is E of X bar. And I could put a little more detail for a sample size of 2, but I won't. What happens if I decide to sample 3 times? Here are all the possible sums. Here is a table of possible sums, again with the associated probabilities. And if I take these and again find the sample average, I just take this number divided by 3, and these are the possible averages. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible averages. If again I do the same process I did a minute ago, taking my output times its probability and repeating over and over and over again, when I sum up these results, I get again negative 0.5, the same as before. Nothing's changed. This is now x e of x bar, but for n equaling 3, all possible values. Notice the number of averages has increased, but each one of these right here is x bar. What happens if I did it again? Sample 4 times. Well, here's the result of all possible samples. Then taken and calculate the probabilities. This 280, for example, corresponds to this one right here, which is a result of taking 70 plus 210, getting me 280, and that's the chance of getting that particular sum. Now here is these values again all placed in a table. If I want to calculate the sample average, all I will do is look over here, the sum divided by 4 this time. And now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 possible sample averages. These are all X bars, or lowercase. What is the average of this distribution? Did I not? Okay, I found my error. This had been positive 40, should have been negative 40, this outcome right here. And once I fix that, here's my average of negative 10, and that fixes this probability, which again, notice it gives you this mean. And so this is again E of x bar for n equals 4. Notice no change. Why is there no change? Because of these probabilities. These probabilities were taken from this scenario right here, and I've been using nothing but these probabilities, and that's what bias is, or bias occurs when you alter these probabilities. If you alter the makeup of the population, if your sampling process is no longer representing the population that you defined, then of course you'll have a biased result. So the takeaway here is that this E of x, the mean of this population, will always equal E of x bar regardless of your sample size. The sample size is irrelevant. But what is changing? What is relevant then if its sample size is not relevant? What's changing is the following. Your averages, your x bars, have a greater chance of being closer to this value as n goes up. Now, we didn't go to a very large sample size, but you can see that true when we look at the table. What is our mean? Negative 50 cents, negative 50 cents. This is in dollars. So right here, somewhere between these two numbers, 5 and negative 10, is the sample, the population average, the mean of this distribution. And again, the outputs are increasingly going to get closer and closer to this as n goes up. So I'm going to just do this once. We'll randomly select from this distribution. So this is a sample of 30. If I take the average of these numbers, I get negative 1.67. Not bad, close to this. This is my x bar, or n equals 30. So these two symbols are not dependent on sample size. This is dependent on sample size. If my sampling process is unbiased, then this should get closer to the mean of this distribution as as n increases. We do it again. Now I find the average. I'm going to copy over here. Yeah, that's not right. Oh, yeah. Sorry. I got 1.9 this time. Again, I noticed I did not get closer. I got a little further away. And this is with a much larger sample size. There's no guarantee. Let's do it again. So there's no guarantee, but the odds are in my favor. If I were to do this again, it should be closer. In other words, it should be closer than this number. So I'm going to be bold. I'm going to do it again. Take a chance. Yeah, so now notice this thing might closer. It's just a matter of chance, but the odds are in my favor. Statistics is not about getting the result you want every single time. Statistics is about getting the result you want a certain percentage of the time. So this is gambling. You're gambling. Let me do it one more time. This time I'm going to change the sample size to 1,000. There is a theory. I'm just throwing numbers right out of thin air. In other words, the sample size I'm throwing out of thin air. But there is a madness to this. You don't just do what I'm doing right here. You want to, what is done is, how close do you want to get to this number? Then we engineer it so you will get close to this number a certain percentage of the time. That's what's really done right now. I'm just making a point. Oops. And I got negative 48. So yeah, that's much closer. I'm now 2 pennies away from that target. So as n increases, x bar will get closer to e of x or e of x bar. Okay, and of course we want these to be equal, but that can only happen as if we have unbiased sampling process, and that's what we care about. All we're getting is this is getting closer to e of x bar. This belongs to this distribution. Uh, you know, the sample averages. This distribution, not this distribution. But the two centers are equal when we have an unbiased sampling process.